Equipment Lesson 6 covers Digital Imaging Systems, CR and DR. This is the longest equipment lesson at 16 minutes. Because digital imaging is the most tested equipment topic on the ARRT, and it's the technology you use every single day. We cover how digital differs fundamentally from film. How CR photostimulable phosphor plates work. Step by step, the two types of DR flat panel detectors. Digital image processing and window and level exposure. Index and deviation index management, common digital artifacts, and CR and DR quality control. Let's build a complete picture. 6 things changed when imaging moved from film to digital. Processing, film required chemical developer. Fixer, wash, dry, taking minutes per image. Digital systems produce an image in seconds with no chemistry. Dynamic range, film had a dynamic range of approximately 25:1. A 14-bit digital system captures more than 16,000 shades of gray, a dynamic range of more than 10,000:1. This is the source of digital imaging's superior contrast resolution. Overexposure visibility, an overexposed film was dark and immediately obvious. An overexposed digital image looks diagnostic on screen. The system compensates electronically. This is the defining challenge of digital dose management. And why the deviation index, D1, exists. Post-processing, film, what you expose is what you get. Digital, window and level, magnification, edge enhancement, and noise reduction are all available after acquisition. Spatial resolution, this is the one area where film outperforms digital. Film screen systems resolve up to 15 line pairs per millimeter. Digital flat panels typically resolve 2.5 to 3.5 line pairs per millimeter. Look at the 6-step workflow diagram on this slide. Computed radiography uses a photostimulable phosphor plate, PSP, as its detector. Step 1, the PSP plate sits inside a cassette. Indistinguishable from a film cassette externally, coated with barium fluorohalide crystals activated with europium. Step 2, X-ray exposure. X-ray energy is absorbed by the phosphor crystals and trapped in elevated electron energy states. This stored energy is the latent image. Step 3, the plate is fed into the CR reader unit, where a low-energy red laser, 694 nanometers, sweeps across the plate surface. Step 4, the laser stimulates the trapped electrons, which release their stored energy as blue-green light, approximately 400 nanometers. This is stimulated luminescence. Step 5, a photomultiplier tube captures the emitted blue-green light and converts it to a measurable electrical signal. Step 6, the electrical signal is digitized and sent to the PACS. The image appears in approximately 45 to 90 seconds. At the bottom of the diagram, the erase cycle. After readout, the plate is flooded with bright white light. Direct digital radiography uses flat panel detectors. No plate handling, no reader, image available in under 10 seconds. 2 detector types are tested on the registry. Indirect DR uses amorphous silicon, AC, with a cesium iodide scintillator or gadolinium oxysulfide scintillator. X-rays hit the scintillator layer and produce visible light. That light hits a photodiode array beneath it, generating electrical charge. The charge is read by a thin film transistor, TFT array and digitized. 2 conversion steps, X-ray to light. Then light to charge. Hence the name, indirect. Cesium iodide is The preferred scintillator because its columnar crystal structure limits lateral light spread, keeping spatial details sharper than gadolinium oxysulfide. Systems. Indirect DR with cesium iodide is the most common DR type in general radiography. Direct DR uses amorphous selenium as a photoconductor. X-rays interact directly with the selenium layer and create charge carriers without any intermediate light step. 1 conversion. X-ray to charge. Hence, direct. The TFT array beneath collects the charge directly. The chart on the left of this slide shows dynamic range across imaging systems, from film at 25:1, up through 8-bit, 10-bit, 12-bit, to current 14-bit digital systems at more than 16,000 shades of gray. That enormous gray scale is what gives digital imaging its contrast resolution. Advantage over film, the ability to distinguish between tissues of very similar density. But displaying 16,000 shades of gray on a monitor that shows only a few hundred requires window and level. Window width controls contrast. A narrow window displays a small range of gray values. Everything below is black. Everything above is white, producing high contrast between tissues. A wide window maps a large range into the display, producing low contrast, soft appearance. Window level sets the center of the displayed range, controlling brightness. The 5 window presets on this slide are directly tested on the registry. Lung window, very wide, approximately 1,500, centered at -600. This wide window handles the density extremes between air and soft tissue in the lung. Bone window, very wide, approximately 2,000. Centered at +2 more columns of essential knowledge for this lesson. Exposure index, EI, is manufacturer specific. It reflects detector dose, higher number means more radiation reached. The detector. Know your department's EI scale and target values for each exam type. Deviation index, D1, is standardized. 0 is optimal. +1 means approximately 25% over target. -1 means 25% under. Beyond +or-3 requires investigation. Monitor D1 on every exposure, not just when the image looks off. Exposure creep deserves special emphasis. As technique drifts upward over months, D1 values slowly rise, but because images still look acceptable on screen, no one catches it in real time. Only systematic D1 audits across the department identify exposure creep. Run those audits. 7 digital artifacts Bill should be able to name 4. The registry. Grid artifact, wrong focal range grid or grid misalignment, parallel lines across the image. Ghost image in CR, incomplete plate erasure, prior image visible through the current one. Dead pixels in DR. Detect 6 QC tests are required for digital imaging systems. Flat field uniformity for DR, expose the detector with no patient or phantom. The image should be uniform brightness throughout. Non-uniformity indicates dead detector elements or calibration drift. Performed daily or weekly. Spatial resolution, a bar pattern resolution target is radiographed. 3 digital imaging questions in the ARRT style. The answer is C, direct DR using amorphous selenium. Direct DR uses an amorphous selenium photoconductor. X-rays interact directly with the selenium layer to create charge carriers, no intermediate light conversion. This direct conversion Preserve spatial information better than indirect systems. Because there is no lateral light spread. It is used. Particularly in mammography where high spatial resolution is critical. The answer is B. The PSP plate was not adequately erased. Before reuse. A ghost image in CR results from incomplete erasure. If the erase lamp fails to release all stored electrons from a prior exposure, those trapped electrons contribute to the next readout, producing a ghost overlay on the current image. The solution is ensuring complete plate erasure and inspecting the CR reader's erase lamp function. The answer is C. Document the elevated D1, investigate the cause, and reduce technique for future exposures. A D1 of plus 2.8 indicates significant overexposure. Repeating an already diagnostic image doubles patient dose without benefit, directly violating ARRT. The correct action is to document, identify the cause, and correct technique going forward. D1 monitoring is how ARRT is enforced in digital imaging. You covered the film-to-digital fundamental shift, the CR. Photostimulable phosphor plate workflow step by step, indirect versus direct DR flat panel detectors. Window and level with the 5 clinical presets, deviation. Index management and exposure creep, 7 digital artifacts. And the 6 QC requirements. Digital imaging is every exam. Know this content cold.